Okay, continuing chapter 13, I talk about waste removal. Waste removal is very much connected to water control because the wastes are particles, and if you want to move water, move particles, shift the concentration of water, and the water will follow, it will diffuse. So a lot of water control involves moving albumin we talked about, but also you can get away with using waste materials to move water around. Now with very small animals, protozoans, that sort of stuff, we're talking about diffusion, right? You make waste materials, they just leave into the environment. For larger animals, you're dealing with three basic products. I'm going to write them down and then talk about them. Okay, these are what you get when you use proteins for energy. First thing you do is you break the proteins apart into amino acids. And then you need to feed the carbon part of the amino acids into respiratory processes because it's breaking carbon bonds that gives you the energy to make ATP. Well, amino acids have things in them that are not carbon. They always have nitrogen. Sometimes they have other stuff too, but they always have nitrogen. And so you have to pull the nitrogen part of the amino acids off, and you get nitrogen and hydrogen stuck on it. That's ammonia. Ammonia is very water soluble, so if there's a lot of water available, it's easy to get rid of. But it's pretty reactive, which makes it potentially very toxic. So in larger animals, you don't really, you need, if you can't get rid of this really fast, you can't afford to leave it wandering around in your tissues. So you need to process it. Sometimes you can process it into a somewhat less toxic and a slightly less soluble form, urea. That's what we do. We circulate urea, we remove it in our kidneys, in our urine. It is slightly toxic though. That's why if your kidneys fail, it will eventually poison you. The buildup of urea will gradually poison you. Now, land animals wound up with a major issue where once they were able to lay eggs out of the water, eggs that were sealed enough that they didn't dry out while the embryos were developing, but they could still breathe. That's quite a neat trick. I don't know if we talked about the amnion or not back when we talked about reproduction. But anyway, they needed to go one better on excretory products. They needed to produce an excretory product that was totally non-toxic, that could build up while an embryo developed, because an embryo is going to develop metabolic wastes, but it would not poison them. And that's uric acid. It takes a little bit more chemistry, a little bit more energy to produce it, but it's really useful to produce a totally non-toxic excretory product. And so reptiles, birds, insects, spiders, millipedes, centipedes, the vast list of land animals that produce sealed eggs, including platypuses and echidnas in the mammal group, produce uric acid. And they tend to keep producing it through their lifetimes. Uric acid is not very soluble at all. You have to kind of move it around in moving fluid because it's more, you move it more as a slurry than as a dissolved particle. And it's a white powder, which is why bird droppings have that white powdery element to it. And the snake droppings in the snake tank have a white powdery element to them. Sometimes you'll hear they produce uric acid because you can remove it without losing a lot of water. That turns out not to be a big issue. And things that have no need to conserve water still produce uric acid. Not really sure where that particular function of uric acid came from. Nephra, N-E-P-H-R, is a root of kidneys, and so it shows up in a lot of these terms. That's an A. In flatworms, the flame cells that I talked about are called protonephridia. Everything comes in through a membrane. It doesn't come from tissue fluid, which makes it a little unusual. I mean, it comes from tissue fluid, but to get into the protonephridia, it's got to come in through a membrane. That turns out to be unusual. That flame, the flagellar tuft, produces negative pressure, and some materials are pulled through that you don't want to remove, so you need to get those back. That turns out to be a common theme in a lot of waste removal systems. In metanephridia, which you get in annelids and mollusks and a few other phyla, is that the wastes are removed from hemolymph, from the circulating tissue fluid. And there are blood vessels that are associated. In the annelids, it's a closed system. In mollusks, it's kind of a weird open-closed system combination. And again, you absorb stuff back that you didn't want to lose that just happened to leave. In a lot of arthropods, there are antennal glands that are up near the front. These are especially in crustaceans. If you eat lobster and people go, oh, I love the green glands. The green glands, you don't think of them as being basically the waste removal system because they're in the heads. But basically, you get those 3 steps, except now you're running through a filter. The body fluid is running through a filter that only small particles can go through. These wastes are small particles. And so you filter it, then you got this material with waste in it, but it's got other small particles that you don't really want to lose, like glucose, pretty good fuel, and minerals, some other things. And so you need to take some stuff back. And there's some things that turn out to be waste materials that won't go out through the filter, but you do need to add to the developing what's going to be removed from the body as waste. So this is the first spot, but not the last spot that you see. I'm going to move it here. Filter, reabsorption, secretion. And these are very, 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 very common steps in all sorts of more advanced waste removal systems. It happens in our kidneys the same way. And we'll get to that. Insects have Malpighian tubules. They kind of wave through the hemolymph. I'm sorry we didn't get a chance to dissect live crickets in the lab, where you can see the Malpighian tubules do their little dancing. But they filter waste materials out and do the same basic thing, and then they produce uric acid, and that goes into the digestive system, the back end of the digestive system, which is a very common theme in a lot of animals. It's added to the digestive wastes to be removed from the body. We have kidneys. In some primitive chordates, it actually winds up being a metameric system where you've got a bunch of these things, but typically there's only a couple of them. And in the kidneys, you have a functional unit called the nephron, the filter, which is called the glomerulus, and the collection space with a drain on it, and then tubules. And again, what are the tubules doing? Well, they are pulling stuff back that your body still needs. Is that glucose? Glucose is your basic fuel. you're always trying to pull glucose back. The only way that the glucose should get out of your body is if there is too much glucose and it overwhelms the reabsorption capability of the tubules. That's why sugar in your urine is an indication of very high blood levels, too high blood levels, because your system is very much set up to take the normal amount of sugar that's in your blood and a little bit more, but you can overwhelm the system. Also, depending on your mineral input and your mineral needs, you may be taking back magnesium, you may be taking back sodium, you may be taking back chloride, or you may just be letting it go. So this is regulated hormonally to some extent, so that you keep what you need to keep and lose what you need to lose. And then there's that set of tubules that take stuff that's still in your blood, wouldn't go out through the filters because the particles are too big, but you need to get rid of it. So again, this filtering, reabsorption in one set of tubules, the front set of tubules, the proximal tubules, and then the distal tubules do secretion of, they add stuff to the waste materials. And so what you wind up with is water and urea, a lot of minerals. We tend to take in more sodium than we use. Hydrogen ions, urine tends to be somewhat acidic. But all stuff that you don't need that you've gotten rid of. Okay, let's see. Okay, well, Gus saw them when he crested the hill. Snakes, 3 of them, basking on the roads, probably diamondbacks. Normally, they'd be on the pavement, picking up the heat from the pavement. They wouldn't normally be on a chase lounge with sunglasses and little reflectors on. But the basic idea that this joke is working off of is that they would be warming up. Temperature. Do you generate your temperature internally or pick it up from your surroundings? Ectotherms pick it up from their surroundings. Technically, they're poikilothermic. Not even sure what the Latin root of that is. Endotherms, these are considered to be older terms. These are considered to be newer terms. Homeothermic. We're homeothermic. We generate a standard temperature, or sometimes a couple of standard temperatures, depending on the animal. Our chemistry is all based on enzymatic speed up of chemical reactions. And enzymes almost always have a temperature range where they work much better. And cooler, they don't work so well. Warmer, they don't work so well. Some of them have a pretty broad range, but tend not to work really great, even at their what's called their optimal temperature. And what we have is a very narrow range of temperatures, but our enzymes work really well at a narrow range of temperatures. But we have to generate the heat to keep that temperature stable. So we have to regulate. I'm just going to call them ectotherms. I'm fine with that. I'm about to give you a list, so don't put it as close together as I'm doing it, because I'm going to step away and give you the list. A lot of regulation in ectotherms and endotherms to some extent is behavioral. You need to get warm, put yourself someplace warm. You need to cool off, get yourself someplace cool. If you need to warm up quickly, if you're a snake and the sun's that way, you orient yourself to pick up as much heat as possible from both the surface you're on and the incoming sunlight. Whereas if you're aimed that way at the incoming light, it's not going to be quite as efficient. When you're active is going to matter. You know, active when it's warm out. There's a lot of ectotherms have double duty, like 2 different enzymes doing the same thing. One of which are usable pretty well at nighttime or burrow temperatures, and some of which are usable daytime warm temperatures. And so they both have their optimal temperatures, but they both drop off going in different, so there's a little trough in the middle where they don't work that great. So you get out of the burrow, when you warm up, you get from your burrow temperature, and then you sun yourself and you lose that enzyme and you pick up the other enzyme, and then you're active in the daytime. That's one of the downsides of being ectothermic. You may need two enzymes to do a lot of different things. And also, you're not hitting your optimal temperatures all the time. Now, some ectotherms do generate their own heat. If it's a cold morning and you see a moth on a wall and you give it a little poke, chances are it's not going to fly away, but you'll see it shiver. It will shiver its muscles to warm them up because they aren't usable unless they're warm enough. But the same way we shiver to generate heat, ectotherms, some of them, shiver to generate heat. In terms of weather like we have, where it freezes, is that some of them can go dormant and survive, find themselves places where they're not going to solid freeze. And some of them produce antifreeze, produce a chemical that keeps crystallization of ice from happening in their body tissues and their cells. For endotherms, there's often difference between our core temperature and our extremity temperatures, right? Your hands and there's a reason why we take our temperature from our core, because the temperature out here is a little cooler. And in fact, this isn't really a core temperature. Most of the thermometers that take this reading are not actually reading the actual temperature. They're reading an adjusted temperature based on what we know this feels like when the core temperature is a certain level. In order to cool off, a lot of animals use evaporative cooling. We sweat, that's a kind of unusual. A lot of animals pant or open their mouths and let a lot of evaporation come off of their respiratory surfaces, especially the upper respiratory surfaces. Is that the hottest molecules are moving the fastest. They escape into the air. They take their heat with them. That is why evaporation is a cooling process. Insulation is a big deal for endotherms that live in cold environments, right? You want to hold on to your heat, not lose it too much to your environment. The best insulation is cheap insulation. Doesn't take much to build. Mostly that is air pockets, little air pockets. So downy feathers or fluffy hair are both very good insulators. Fat is a pretty decent insulator, but it's metabolically expensive. So you don't see fat as an insulator except in animals that can't afford, it's not that they can't afford, they can't really use feathers and hair effectively. These tend to be deep divers. If you watch fur seals dive, as they go deeper, you can see bubbles come out of their fur. It's because the pressure of the water is squeezing the air out of their fur. They're losing their insulation of that fur, so they don't dive very deep. See that in penguins too. Most fur seals also have a layer of blubber underneath so that they do have that supplement, so do penguins. But something like a walrus that doesn't have any hair at all, it's all blubber. Deep diving whales, all blubber. But they can't use it, the fat for energy, which is another thing we use fat for, because it's keeping them from losing their heat to the water. Water is a tremendous heat sink. It absorbs heat really, really effectively. So if you're going to be in water that's below your body temperature, you got to keep from losing too much heat, or you got to generate a tremendous amount of heat inside. Burrows are pretty effective as a way of keeping yourself from getting too cold. Nests. Snow actually is a pretty good insulator. Around here, a lot of animals store food in their burrows expecting when it gets late enough in the winter that we get a lot of snow, they'll come out and forage under the snow because the area right at the ground level isn't as cold as the air above the snow. Snow's got a lot of air pockets. It's all loose. It captures air pockets. In years where we don't have a lot of snow, it can be a killer on small burrowing animals that haven't stored that much. Is that they come out ready to forage and they freeze because they don't have their little bodies. They're not well insulated. We get That countercurrent system of heat exchangers again. Think of a duck paddling in the water. Water's pretty cold. If you ever look at a duck's legs, no insulation. What they do have is the blood going out is passing the blood coming in. So this is hot, this is cooled off. This hot is warming the incoming blood, and it's getting cooler as it goes. And as it's cooler, it's going past even cooler blood. And so you get this countercurrent exchange system where the heat moves from, this blood is warming up. It's still cooler than the blood right coming out of the body. And so by the time the blood gets out to the feet, it's cooled off quite a bit. By the time the blood gets back into the body, it has warmed quite a bit. So you're not losing anywhere near as much heat to your watery environment for your flippery feet as you would be otherwise. There are also animals that will go dormant during winter. They hibernate, and their temperature goes down, conserves energy, conserves, stored energy. And some animals go through what's called daily torpor. Some bats will do this, where hanging in a cave, their body temperature will drop pretty significantly. And again, they save energy. They're flyers. They've got a lot of energy needs. Anything that helps conserve energy is useful. Okay, that's it for this chapter.